Yeah, so the sign up link is tinyurl.com/CBA ProfCon22. So CBA PROFCON22. Yeah.
Thank you. It'd be great to see any of you there.
And if anyone wants a flyer, you can put your hand up. I can give you a flyer.
If you guys didn't get that link, it's also on the ed post under data science opportunities. So if you want to just take a look at that, there's some data science opportunities that are coming up. There's also, I don't know if you guys have heard of a hackathon, but there's a datathon that's coming up. So make sure to check out that ed post for any cool data opportunities that are upcoming.
Okay, let's get started. Data 8 lecture number 30. Can you hear okay in the back? Unclear. How about now? Is that better? You hear okay in the back? Announcements. Homework 9 is due today. Project 2 checkpoints due Friday. We will have a project party tomorrow, 12 to 5 in Warren. And the full project is due next week, but you get an early submission bonus point for submitting it by next Thursday. So definitely get started this week so you can get the checkpoint in and you can finish the whole thing early. Questions? Okay. Last lecture was about the correlation coefficient, referred to commonly as R. Here are some examples of scatter diagrams and the correlation coefficient between X and Y, where you need a whole data set of XY pairs in order to compute such a thing. This was an example where R was 0. And recall that this was not the only example where R was 0, but one of them. When R is slightly above 0, that means you get an upward sloping shape of some sort. R at 0.5 gives you something that is kind of more organized around an upward sloping line. And as R gets larger and larger, the scatter diagram looks a little bit more like a line. R can also be negative, and when it's negative, the shape is downward sloping. So there are more dots in the bottom right and the top left, and the bottom left and top right are generally empty. This is a measure of linear association. You saw last time that there can be an association that's nonlinear, and you can still end up with an R of 0. It's based on standard units. The nice thing about standard units is that you don't have to worry about what original units the data were measured in. You're going to get the same standard units regardless of what original units you measured it in, because they're an expression of the variability within the data. R is always from -1 to 1. R equals 1 is a scatter diagram that is a perfectly straight line sloping up. R is -1 would be a perfectly straight line sloping down. The fact that this has a little bit of variability around a line means that R is not 1, but you can see it's pretty close to 1. When R equals 0, that means there's no linear association. You can say that X is uncorrelated with Y, or X and Y are uncorrelated. And the definition of R involved computing Y in standard units. That means that each value in standard units is telling you how many standard deviations above or below the mean of Y a particular value is. You also have to compute X in standard units. Then you take the product of the X values and the Y values for the different values and average those, and that's how you get the correlation coefficient R. So this is like one of those things to memorize. Okay. Measures how clustered the scatter diagram is around a straight line, either sloping up or sloping down. Let's see if we can interpret this correctly. Discussion question, true or false. If the correlation of X and Y is close to 0, then knowing the value X for a particular subject cannot help us predict the value of Y for that subject. Discuss. Okay, thanks for discussing. The answer in this case is, since it says knowing one cannot help, the answer is false. It might be the case that you can do a good job of predicting Y from X if it turns out that the association between X and Y is nonlinear. You did see one example of this last time, I believe, where, let's see if I can pull up the picture. Was this picture. In a data set that looks like this, if you told me the X value, I could tell you the Y value because I could look at all the other points and see, oh, they all fall nicely on this parabola. But it turns out there's no linear association between X and Y in this case, just because of the definition of the correlation coefficient, which I think we should take a moment to define together, and then we can check that this is true. So let's remember what it means to convert to standard units. You need to subtract out the mean. And then you need to divide by the standard deviation. Now you've converted a whole array of x values into standard units. If you perform that operation on the whole column x and the whole column y of some table of xy pairs, then you can compute the correlation between x and y in that table by computing the average of the product. NP dot mean of x in standard units times y in standard units gives you the correlation coefficient. Once we've done that, then we can look at this nonlinear example, which has x's and y's, and we can compute its correlation. We'll find it's 0. But knowing x tells you a whole lot about y, because once you know x is 2, then you know y is 4 in this association. However, there's no line I could draw through here that would tell me what the relationship is between x and y. So that's why we say there's no linear association or no correlation between that particular xy. Questions? We're like 8 minutes in. I must have confused some people. What's going on? Okay. Yeah, in the back. Okay, the answer is false because there is a scenario out there in the world where knowing the x value tells you the y value or tells you a good guess about the y value. It doesn't mean it's always the case. So for example, if this were my scatter diagram, then I would have agreed that knowing x doesn't really help you predict y. But it turns out there's other scatter diagrams that also have an R of 0 where you can make a prediction, and that's because there's a nonlinear relationship. Whereas this scatter diagram is when there's really no association of any kind. Excellent question. Today we're going to figure out how to use correlations in order to make predictions. We've actually seen a little bit of this earlier in the course, but now we'll learn kind of the standard methodology for using lines in order to make predictions of y values from x values from a data set that has xy pairs. The method that we're going to talk about today really only works if we have a data set, so many observations, that have some kind of oval shape. What do I mean by an oval shape? I mean, you look at the scatter diagram and you can see that, yeah, there's like some variability. The dots are all over the place. But if I were to, characterize what's going on here, it seems like there's some sort of oval shaped distribution where all the points fall in that oval. And on the border of that oval, there's a few points, but way outside of that oval, there's nothing. Here's a moderate positive correlation. The place where we saw this before was that once upon a time, Francis Galton went around measuring the heights of different people in families, and what the measurements included was for each child who was at that time at their adult height, but they were, their parents were still around. They measured the height of an individual adult child, and then they measured the average of the heights of the parents and had one dot for each child. Remember, this is like an adult-aged child, but so I should stop calling it a child. It's an adult. Measured each adult and then measured the average heights of the parents of that adult and placed that on the scatter diagram. We looked at this example earlier in the course. What this has to do with prediction is that if we found a new pair of parents, which we thought were part of the same distribution, and this was a sample of that distribution, then we might try to guess if they had a child, how tall their child would be upon reaching adulthood by using this scatter diagram to make an estimate. We've been making estimates for a while now. We've even gotten so sophisticated that we draw confidence intervals and stuff like that. Well, now we're going to try to make estimates that are based on knowing an x value and guessing a y value. So how can we predict child height from parents' average height? And the approach that we used earlier in this course was to look at other parents that had a similar average height. And we drew the following diagram. Does anyone remember this diagram? Some, but some do not. Okay, let me tell you how we got here. This diagram was generated by going through every point, taking all the points that were near that point, meaning close on the x-axis, and averaging the y values. And we even gave this a name. This was the graph of averages. And this graph of averages turned out to expose something that looks kind of like a line. Now, you might not agree that it looks like a line because it's definitely bumpy, but it's also kind of a line. It looks more like a line than a parabola or a sine wave or a squiggle or something else. And that's just an interesting property of the data, that if you go through for every point and you find nearby points in terms of their x, and you average those, then you end up with a position on y. And if we do that for every point, we end up with a bunch of dots on a line. This was called nearest neighbor regression. It's a method of prediction where we group each x with similar, meaning nearby x values, average the corresponding y values for each group, and for each x value, the prediction that we want to give is the average of the y values in among the points that have similar x values. So the nearby group is the one that we got when we grouped each x with similar x values. Why this is interesting for prediction, if we're trying to predict y from x, is that for the example you want to make a prediction, you need to know its x value, but you don't need to know its y value. You need to know its x value in order to find among the group where you have the whole scatter diagram similar x values and look up their y values so you can average them, but that allows you to come up with a guess for y without knowing it in advance. And the graph of these predictions is called the graph of averages. If the association between x and y is linear, then it turns out the points on the graph of average tend to fall on a line. So for all those different scatter diagrams that had linear associations, if I draw this graph of averages, it's going to end up drawing a line, or something like a bunch of points that are near a line. Question? Good question. Does it have to be football shaped, oval shaped, or does it just have to have some linear association? For the graph of averages to fall along the line, it does have to be oval shaped or football shaped. If there's a correlation, but also there's like some other weird structure going on, then the graph of averages won't fall along a line. It will be some other weird shape. Good question. What does it mean to group x with a nearby x value? When we did this before, we made an arbitrary choice that said when all the points that were within a half an inch of average height. And so anytime you perform this method to form the graph of averages, you have to make an arbitrary choice. And you want to pick it so that it actually does get some points, but not so many points that it's not nearby anymore. So yeah, there's no one answer. Instead, you'd have to look at the data to figure out what the right measurement is. But when it comes to human heights, yeah, like a half an inch might be a reasonable choice. Now, the interesting question is, when r is some value, and we draw some football-shaped thing, some linear association, where does that nearest neighbor line actually fall? Well, let's try it out. We'll try it out for when R is 0.99. We'll try it out for when R is 0. We'll try it out for a bunch of different values, and we'll discover something interesting. Okay, so I've written a bunch of code that I'm not going to go through that actually just generates random data. Instead of using real data, we're using random data. The reason we're using random data is so that I can pick the R, the correlation coefficient, in advance and get a scatter diagram that has that R. So I know this is not like a useful data science skill, but it's going to teach us something interesting about nearest neighbor prediction, and then we can use that in order to draw lines. So here was an example when we set R to be 0.99. How would we draw the graph of averages? Well, we need some way to pick out all the neighbors. So we take our example table, and for this particular X value, we want to find all the X's that are near that. So what do we mean near that? Well, we'll just say between that X value minus a little bit. How about 0.25 and plus a little bit? X value plus val plus 0.25. So why did I pick 0.25? I kind of just like looked at this picture, and I feel like 0.25 is just like a narrow little area around any particular X. So hopefully it'll work. So now we've picked out all the ones that are near in terms of the X. Those are the neighbors. What is the prediction that we make? Well, that is the average value of those neighbors' Y values. And prediction for a particular value like 1 turns out to be pretty close to 1, okay? And if I made a prediction for -1, I got some value that's pretty close to -1. So that means if I go out here, it looks like when I go 1 on the x-axis, and I get about 1 on the y-axis, and likewise, if I go -1 on the x-axis, I end up around -1 on the y-axis. The graph of averages comes from drawing all of them. So build example table. Looks like this. It has X value, Y value. We're going to add a column. The predicted Y value. Now this is weird because we already know the Y value. Why would we predict it? It's because we want to see what would happen. We want to see where the graph of averages would fall. And the first interesting thing about it is that it sure looks like a line to me. So I claimed that when you have any kind of oval-shaped or football-shaped scatter diagram, which is linearly associated, and you draw the graph of averages, then the points are going to fall along a line. It's not perfect, but it's pretty dang close. And if we look at the line that it draws, and we actually just draw a line with a slope of 1, seems like they're pretty close together. Okay, that's cool. Let's try the whole thing with R equal to 0. We're okay? Now when we make a prediction, X is 1, what's R, what's Y? Well, it's about 0. If X is -1, what's Y? Well, it's about 0. X doesn't tell you anything about Y in this case. If we add the prediction column, and we draw the graph of averages, it's a line. Except it's a line with a slope of 0. Now you're wondering, how come it's not a line out here? Well, we just have very few observations around here, so we're getting a bunch of random noise. But in the center, where most of the dots are, it's pretty much a line at 0. And so if we draw that, and then we draw the y equals x line, we find that they're nowhere close to each other. Okay, that's not a big surprise, I don't think. But before I do 0.5, I figured I'd see if there are any questions. Okay, let's do 0.5. In the real world, if you're trying to predict some y from some x, it's unusual that you'll get a 0.99 correlation. Much more common that you'll get a correlation coefficient that's like half or like a third or something like that, which gives you a scatter diagram that might look something like this. If we make our prediction examples for every point, and we draw the scatter diagram where the blue are the original points and the gold are the graph of averages, then we see something that looks like a line. But what's interesting about this line is that it's not the y equals x line. Let me show you something. What if we wanted to draw a vertical line out here at 1.5? When x is 1.5, the blue line says 1.5. But where's the gold line? It's actually down below 1. It's at 0.75, which is half of 1.5. So if I go out 1.5 from 0, I go up half of 1.5 or 0.75. And why is it half? Well, because r is a half. This picture is meant to show you an interpretation of the correlation coefficient. It's the slope of the graph of averages. Let's draw another line. Let's draw a line. This time I'll make it red. And I'll give it a slope of 0.5. It goes right through the graph of averages. But it's very different from the y equals x line. So the way I would make predictions is if I knew the x value was 1.5, I wouldn't predict that the y value was 1.5, even though there's a positive correlation. Instead, I'd look at the correlation, which is a half, and I would say, okay, then if x is 1.5, then y is half of that, 0.75. That falls along the red line, which is the y equals r times x line. And that would correspond to my nearest neighbor prediction approach. Yeah. Okay, I almost got the question. Can you say it one more time? Oh, great question. So why are we taking the average over y values, and what does that have to do with the slope? We're trying to make a prediction for an individual, like how tall are they going to be? But we just don't know. They're going to grow up and they're either going to be, 3 standard deviations above the mean or 1 standard deviation below the mean. Any particular kid could end up anywhere. But we're trying to make a guess. So a reasonable way to make a guess is to say there's some distribution, and I'm going to guess the average of that. So that's why we average the y values in the first place, is that if we were given only an x, only the parent's height, for example, and we wanted to guess the y, how would we do it? Well, we'd look at all the y's around there, and we'd take the average because that's a good way of making an estimate. Like if we're going to predict something, it makes more sense to predict the average than the max or the min or some random number or something like that. But we're not taking the average over the entire data set. We're only taking the average over the points that have a similar x. So the reason we got this graph of averages, which are the gold dots in the first place, was that we performed this averaging operation. And we did it for x equals 1.5, and we got a gold dot that was right around here. We also happened to do it for every other x value, and that's how we got the other gold dots, and we saw they fall on a line. But right now we're concerned with what happens when x is 1.5. What should I guess as a reasonable estimate for the average y that will come out? And the answer is the average y that actually did come out is 0.75. And so that's a good prediction that we might use if we had to guess what a y value is for someone whose parents' x value was this. I don't know if I answered your question or not. I tried. Oh, great question. So we saw this formula for R and it kind of came out of nowhere. Like it's like converting to standard units and then multiplying things together. Couldn't we derive it from some goal or something like that? Yes, but not till Friday. That's kind of like how we're going to go back and check this out, is that we're going to see that there's kind of an optimization based approach to getting this line. But what we wanted to show you first is that R is a standard statistic, like descriptive statistic of scatter diagrams that people compute. It's just describing what degree of linear association there is. And it's not just some arbitrary number. Instead, it appears as the slope of the graph of averages when you draw the graph of averages and there's actually a linear association. Let's try one more time. 0.7. Scatter diagram is more closely concentrated around a line. But what line is that? Well, we'll draw the graph of averages. We see a line, that's good. But what's its slope? Well, the red line's at 0.5. That sure doesn't look right. If I set the red line to 1, that doesn't look right either. But if I set it to 0.7, which is the R for this data set, then we can see that that red line goes right through the graph of averages. It is the line that describes the average y value for each x value in a linearly associated data set. That's cool. Okay. What else do you want to know? Otherwise, we'll do it with real data. Which reference? Or is it like out of date somehow? Oh yeah, so we're learning some new functions. We're like writing stuff down, like how to compute standard units and stuff like that. We do give you a final study guide that has all of this stuff on it. Oh, do you want it sooner? Yeah, we can get it to you sooner. We usually give it to you right before the final, but maybe you want it now. That's a good suggestion. Can we make that happen? I bet we can make that happen. Okay. Great idea. So the ones that that we've hit so far are the standard units calculation and the correlation calculation, and we'll do a couple more pretty soon. Other questions about this picture? Linear regression, instead of using the nearest neighbors in order to compute the graph of averages and use that, just says, let's find a line and use the line directly. Now you need an equation for that line. And the way in which you form that equation is by computing the correlation coefficient and then estimating your y, or your average y, by using a particular value of x and multiplying it by r, the correlation coefficient. This is a statement about x-y pairs that says that if you measure x in standard units, you can describe the deviation of y from 0 based on the deviation of x from 0. Now, what is 0 in standard units? It's the average. So it's just measuring how many standard deviations above or below the average you are in x. And you're describing the deviation of the corresponding y value. So you're looking at an individual there's some X for them, there's some Y for them. You know their X, you don't know their Y. You're trying to estimate their Y. You've decided to estimate it using an average. An average among others in the sample who have the same or similar X. And you do it using this equation for a line as opposed to actually finding the graph of averages, which is like some wiggly version of the ideal line. On average, V deviates from 0 less. Oh, sorry, that's not a V, that's a Y. Why does it look like a V? Should we fix it? Maybe we should fix it. Oh, it's super hard to fix because I only have read-only X's. Well, that's a Y. Okay, you'll have to believe me. There's so many people looking at this right now that it won't let me edit it. Okay, so on average, Y deviates from 0 less than X deviates from 0. What is this sentence? On average, Y deviates from 0 less than X deviates from 0. Well, R is some number less than 1. So if X is 2 standard units and R is a half, then Y is only 1 standard unit. That's closer to 0 than 2 is. This is also not necessarily true for all points. It's a statement about averages, the average Y value for a given X value. This idea that on average Y deviates from 0 less than X deviates from 0 is called the regression effect. Now, we've done everything in standard units because it's really easy to write the regression line in standard units. It's just Y equals R times X, which is different from Y equals X, but it's still pretty simple. You might want to write that same line in original units. So here's what we've written on the last slide. This is Y in standard units equals R times X in standard units. Except now I've written out what standard units means. It means the estimate of Y minus the average of all Y's divided by the SD, the standard deviation of Y's, equals R times the X that I observe minus the average of all X's and the standard deviation of all X's. That's Y in standard units, that's X in standard units. But this is not a typical way to describe a line, because here's your Y and here's your X. And normally you want to write your Y in terms of some constant times X plus some other constant called the slope and the intercept. But that is not what this equation looks like. So we would need to isolate estimate of Y on the left side and collect some terms in order to get it to look like this. Before we do that, I just want to show you what's happening. When you're in standard units and you have a scatter diagram, it's always the case that 0, 0 is at the average of X and the average of Y, because that's how standard units work. And when you draw the regression line, it always has a slope of R, meaning when you go over 1, you go up R. And if you go back 1, then you go down R. In the original units, 0, 0 might be somewhere else completely. It might be way over here or way up here or way over here. You just don't know. It depends what you're measuring and how you decided to measure it. But what you do know is that the average of X and the average of Y is some point in the middle of this scatter diagram. So all we did when we converted to standard units was kind of center the graph axes in the middle, or the average X, average Y, of the scatter diagram. And while the slope is really simple in standard units, it's always R. In order to find the slope in original units, you have to take R times the standard deviation of Y and divide it by the standard deviation of X. which basically is scaling the axes in the horizontal and vertical direction so that they match what it looks like in standard units. If you look at this picture, then you can work out the equation for the regression line in original units, but we'll do that together in a minute. Question? The question is, does the regression line always pass through 0, 0 if x and y are in standard units? Yes, it does. Oh, why is that the case? Well, the goal of the regression line is to match the graph of averages. 0 in standard units is the average. And like when you're at the average x, then you guess the average y. Excellent question. Okay, so what's the regression estimate? Our goal is to predict y using x. To find the regression estimate of y, we can convert the x into standard units, multiply by r, and that's the regression estimate of y, but it's in standard units of y, and so we have to convert it back to the original units of y. That's how you perform regression. The quick way to do it is to say that the estimate of y, if you want to write it down as slope times x plus intercept, is that the slope of the regression line is r times the standard deviation of y divided by the standard deviation of x, and the intercept is the average of y minus the slope times the average of x. How does this get derived? Well, instead of showing you a bunch of algebra, I'll just tell you that it's translating this picture in original units into this picture in standard units, and it's doing this process. If you just go through and convert x into standard units, then multiply by r, and then convert that y value, r times x, back into original units, you end up with a y that's equal to r times the ratio of the standard deviations times x plus the average y minus this slope that you already computed times the average of x. So a lot of times students will see these two equations and think, well, there's a lot of dark magic going on in linear regression. But knowing where it came from, which is that it happens to be that this r tells you the slope of the graph of averages in standard units. And all this stuff of making ratios is just so that the conversion to standard units multiplying by r and converting back to original units happens to fit nicely into this shape of an equation. Y equals slope times x plus intercept. You end up with something that's fairly complicated. Okay. Let's try it out in code. The slope. If you have a table of x, y values, and this is your x label, and this is your y label, involves computing the correlation, which we already did, computing y in standard units, computing x in standard units, and then writing down the equation that I just put on the slide. The intercept, if you've done that, involves computing the y average and the x average and the y average, and then writing down y average minus the slope, which we just computed, times the x average. So, for example, in our data set, which has an r of 0.5, if I ask what's the slope, it's going to come out at 0.5. Why did it do that? It's because the data set that we generated had a standard deviation of 1 for both x and y. So these canceled each other out. But this won't necessarily be true if your original data in its original units has a different standard deviation, then you're going to end up with a different slope. So when you switch to real data, where the standard deviation is not necessarily 1 for X or Y, all of a sudden, the slope of your regression line is not just R, it's influenced by the variability of the different variables. Okay, so let's go back to the real data. We had this table from long ago where we had a column for parent average height and a column called child, which was an adult height of some person whose parents were on average a little bit shorter than them in this case, and a little bit taller than them in this case. And the reason the first 4 rows all had the same parent average is that these are all siblings that had the same parents. We can write down the nearest neighbor prediction approach, which was to say that for any particular parent average value, we can find all of the observations where the parent average is really close, within ½ an inch, above or below, and average the height of the children in that case. So that's the same nearest neighbor prediction approach that we did for our made up data, except now we're doing it on actual observations. And that means for every row in the data set, we can get a nearest neighbor prediction. Notice that for all the children that have the same parents, we have the same prediction. Why is that? Because parent average is the X value, and this is based only on the X value of the particular row we're looking at. So it's based only on this. If we draw the scatter diagram, we see the graph of averages is more or less a line. But can we draw that line? That's what linear regression is about. I'll pause for a second, see if we have questions, then we'll draw the line. Okay. In order to get the slope of this line, we just call the slope function that we defined, but we have to do it on the right table with the right X value. Here's the label for the X values, and the right Y value. We just compute the intercept. So these are kind of generic operations. They don't need to know what the data are about or even how they're measured. Just for whatever units they're measured in, you can compute the slope and the intercept. What's convenient about having the slope and the intercept is then you can draw a line like this. You take the slope, you multiply it by the X value, you add the intercept. This is the thing we just computed. This is the thing we just computed. And if we do that for every X, now we get not just the nearest neighbor prediction, but the prediction from linear regression. Notice they're pretty similar. Can we see how similar they are? Well, if we draw a scatter diagram, we'll see that the gold dots, which were from nearest neighbors, are around a line, but not exactly on a line, whereas the light blue dots are exactly on a line. And they're exactly on a line because the way I created them was using a linear equation. I used a line to make them. But the fact that they're a line that matches the graph of averages is because I chose the line in this particular way. I computed the slope and the intercept according to this particular approach, which involves converting y to standard units, or x to standard units, multiplying by r, and then getting that value, converting it back into original y units, and you end up with this line. Huh? This graph is in original units. This is measuring the parent's average height in inches. This is measuring the child's height in inches. And so you'll notice that it's not centered on 0, 0. It's like 0, 0 is way down here somewhere. However, the average parent average is here, and the average child is here in the center. What we've drawn is the regression line in original units, which we did by calling the slope and intercept functions, which were fairly complicated. To get the slope in original units, we had to not just compute correlation, which was a fair amount of work, but also adjust it for the standard deviations of the y and x when they were measured in inches. The question is, should you memorize the formula? I would say yes, but it's also a good skill to be able to derive it. How would you derive it? Well, you could dust off your algebra skills and start with this. This is really what you want to memorize, is that regression line is about saying that y is r times x in standard units. Once you can write down what standard units are, then you can try to isolate y in terms of x times something plus something else. Okay. This course is not really about doing algebra. It's about understanding the consequences of performing stuff like this. So let's see how far we've come. If you're taking a course and the average on the midterm is 70 and the standard deviation is 10, and then there's a really hard final where the average is 50 and the standard deviation is 12. And you look at the scatter diagram, and it has an oval shape, and the correlation coefficient is 0.75. Then what do you expect the average final score would be for students who scored 90 on the midterm? This is now a question you should be able to answer. And instead of making you discuss it, since we have 1 minute left, we'll discuss it together by listening to me. You see this number 90, that's in original units, that's points on a midterm. You want to convert it to standard units, which means subtracting the average, now you're down to 20, dividing by the standard deviation, now you're down to 2 standard deviations above the mean on the midterm. On average, students who got 2 standard deviations above the mean on the midterm will get only 1.5 standard deviations above the mean on the final due to the regression effect. That's what happens with linear association. Now, 1.5 standard deviations above the mean on the final means they'll get 50 plus 18 is 68 points. You're telling me you got a 90 on the midterm and we're going to guess that you get 68 on the final? Well, yes, because the final was really hard. And the regression effect means that among students who are way above the mean on one exam, if you try to guess their average on another exam, it's going to be closer to the mean. So the answer would be 68. And we'll keep doing problems like this on Friday. See you soon.